Okay, quiet down, please. Okay, before we get started with the lecture, I just have an announcement from Dr. Chetty. The students that were emailed yesterday or today, you need to stay behind after the lecture. So Dr. Chetty is going to be talking to you. Okay, so if you emailed yesterday or today about the TechCom, please make sure you stay behind. Dr. Chetty needs to talk to you. Okay, do you know what that means? You got the emails? You did get the emails. Okay, so those that got the emails, please make sure you stay behind for that meeting. Okay, so we're going to continue with our work on approximations. So last time we looked at the Taylor polynomial or the Taylor approximation. Sorry. So we looked at the Taylor approximation. We did the whole derivation with that, and we looked at a few examples. Now we're going to use that in our applications for function approximation. So we're going to have some function, and we're going to approximate it and look at the error involved in that approximation. Okay, so the Taylor approximation. So we had some function f of x. Okay, this might be some complicated function. What we want to do is approximate it by some polynomial. Now we did this at x equals 0, and we got the following. So this is approximately equal to the Taylor polynomial p, which was given by the sum as k goes from 0 to n, the kth derivative at 0 over k factorial x to the k. So we did the derivation for this, we found the coefficients, and we did a few examples. Now this only worked at x equals 0. Okay, so for all of those examples, we did the approximation at x equals 0. Now, if we want to do the approximation somewhere else, we need to shift across. So here, where we see the x, we're going to shift across to this new point. So let's say we want to do the approximation at x equals c. We're going to take x, we're going to shift it across to x equals c, and then we're going to do the derivative at x equals c. So here we can have the polynomial p as the sum from k equals 0 to n. We're going to have the kth derivative at c, because we're moving everything over to this new point x equals c, over k factorial, and then we're going to have x minus c to the k. Okay, again, we're just shifting everything over to x equals c. So it was at x, then we minus c, so that's a right shifting, and now we're at x equals c. Yeah, and since we're at x equals c, the derivatives now need to be at x equals c as well. Okay, so this was the general formula that we got for any nth derivative approximation. However, now we're going to look at two special cases, the linear approximation and the quadratic approximation. Yeah, of course, you can do higher approximations, but we're only going to be looking at these two special cases. So two special cases. So number one is the linear approximation. Okay, and then for this special case, we don't call it P, we give it the special name L for linear. So this will be L of X instead of the P that we use for the general case. And this will be F at C plus F prime at C, X minus C. So we only go up to K equals 1 instead of K equals N. And then the second special case is the quadratic approximation. Okay, and this special case is given the name Q for quadratic. Okay, and now we only go up to n equals 2 because it's quadratic. So this will be f at c plus f prime at c, x minus c. And now we go up to the quadratic term. So this will be plus 1/2 f double prime at c, x minus c squared. Okay, so these are just the two special cases that we're going to be looking at. Okay, of course, we still have the general case. We can do cubic, we can do to the power 4, and so on. But most of the time, we're going to be looking at these two special cases. So the linear case, or the linear approximation, where we only go up to n equals 1, and then the quadratic approximation, where we go up to n equals 2. Okay, so let's have a look at some examples. Okay, so first example, number 1. Find the linearization of the function f of x equals root x plus 3 at the point x equals 1. Okay. Now, linearization, that's just another way of saying the linear approximation. Yeah, so it's got the word linear in it, so we're going to do the linear approximation for this. So to find L of x, we need the function value at c, and we need the first derivative at c. And in this case, c is 1, because we're doing it at the point x equals 1. So firstly, what is f of 1? So that's going to be the root of 4, and that will just be 2. Okay, so that's the first bit done. Now we need the first derivative at 1. So the first derivative, we can work that out. That's going to be 1 over 2 root x plus 3. Okay, so that's just the general first derivative. Now we want this specifically at x equals 1. So f prime at 1, that will be 1 over 2 times 2, so 1 over 4. Okay, and that's all we need for the linear approximation. The function value at c and the first derivative at c. So we can write out L of x. This is the function value at 1, because we know c is going to be 1, plus the first derivative at 1, x minus 1. So here c is 1. Okay, and then we can substitute what we know. F at 1, we know that is going to be 2. F prime at 1, we know that's going to be a quarter. And then we have x minus 1. Okay, now you can leave it like that. That's perfectly fine. Or if you want to simplify, we can write this as 1/4 x plus 7 over 4. Okay, so that's just simplifying the minus a quarter plus the 2. Okay, but that's not needed. You can leave it at the second step where you do the substitution. That's perfectly fine. But maybe there's follow-up questions, and having it in simplified form helps a bit. Okay, so just take it case by case. Okay, any questions on this one? All good. Okay, let's look at another example. Okay, example 2. For what values of x is the linear approximation okay, so we've got some linear approximation here. It's going to be the same as the part 1. So 1/4 x plus 7 over 4 to the function f of x equals root x plus 3. Okay, so same setup as before. Accurate to within a half. Okay, so follow on from the example 1. We've got the linear approximation. We know what the function is. Now, what we want to do is find the x values. So some minimum x value to some maximum x value where the error is less than a half. Okay, so that's what we mean by this approximation being accurate to within a half. We want the error between the approximation and the function to be less than a half. Okay, so we have the error. This is just going to be the difference between the function and the approximation. Okay, that is the error. So that's going to be f of x, that's our function, minus the approximation, and then we put absolute value. So we don't care if the error is positive or negative. We just have some error, which is the function value minus the approximation value. Whatever that difference is, that's the error. And we want the error to be less than a half. So we want all of this to be less than a half. Okay, so that's what we mean by accurate to within a half. We mean the error is less than a half. Any issues with that? No. Okay, so let's substitute the function and the approximation. So the function value, that's just root x plus 3, that's given. Okay, minus the linear approximation, that's also given, but you may need to work that out separately. Okay, but in this case, it's given to us. So that's 1/4 x plus 7/4, absolute value less than a half. Yeah, and the idea is to solve for x. We're going to have some minimum x value up to some maximum x value. Solve for x. Okay, and the idea is we're going to have some range like that. So we're looking for those a and b values. So between a and b, the error is less than a half. Outside of that interval, the error is then greater than a half. Okay, so we want to find that interval there. Okay, if we have the absolute value of something less than a half, that means whatever that something is lies between minus a half and a half. So we're going to have minus a half is less than that something inside, all of that there. X plus 3 minus 1/4 x plus 7/4. And this is less than a half. Right, that's just using your absolute value properties. We covered that several weeks ago. Now that minus in front of the brackets there, we can distribute that out. So we're going to have minus a half is less than root x plus 3 minus 1/4 x minus 7/4 less than a half. Okay. Again, the idea is still solving for x. Okay, we can do a little bit of rearranging here. So I'm just going to take this root out from the inside there. So minus root x plus 3 for all three parts. So we're going to have minus a half minus root x plus 3 is less than minus 1/4 x minus 7/4 less than a half minus root x plus 3. Okay, so we're just trying to simplify this before we solve for x. Okay, so it's a little bit simpler. Now we've got a lot of minuses going on. So for the first term, we've got 2 minuses. Second in the middle there, we've got 2 minuses. Third one, we've got a minus there. Let's multiply all 3 by minus 1 so we can clear that out. Okay, so all 3 parts, we're going to multiply by minus 1. And then remember the inequalities flip when you do the minus 1. Okay, so we're going to end up with root x plus 3 minus a half is less than 1/4 x plus 7/4 and that's going to be less than root x plus 3 plus a half. Okay, so we just cleared out all of those minuses there. Yeah? Yes?
Wasn't it also supposed last time?
Yes, I also said the inequalities flip. So that first one goes to the second, and then the second one goes to the first. Okay, now we covered this weeks ago now. If you have minus a less than minus b less than minus c, what happens when you multiply through by minus? It goes c goes to the front, then b, then a. It swaps.
So then half over there. Your half in the first part.
Yes.
Isn't it supposed to be positive now, but you flip it over negative?
No. We're looking at the third one. The third one goes first. The first one goes to the third one. The inequality swaps. So the biggest one becomes the smallest one, and the smallest one becomes the biggest one. Okay, now please go to your notes from the algebra stuff. Okay, now I can't waste time going through that. There, here. Minus a less than minus b less than minus c. Multiply through by minus 1 and see what you get. Do it? Yeah, write it out. So minus a less than minus b less than minus c, and then multiply through by minus 1. What do you get?
What is it? J equal to C.
Yeah, what's the order? What's the ordering? Yeah, what's ordering? So what less than what less than what? Write it out so you can to see. Okay, I already warned the class before about the algebra. During the mid-semester break, I said go back over your algebra stuff. Okay, I can't spend half the lecture saying why inequalities swap. Do you multiply it out? So what do we get for the ordering? Yes. So where does C go? Yeah, because the thing swaps. Okay, please, if you don't understand that, please do the working on the side. Okay, so we end up with this. Now I'm going to split this into two problems. We're going to do the first inequality on the left, and then the second one on the right. Okay, so we'll split this up into two. So we're going to have root x plus 3 minus a half is less than quarter x plus 7 over 4. So we'll treat that as one inequality. And then the second one we'll do on the other side. So we're going to have 1 quarter x plus 7 over 4 less than root x plus 3 plus a half. Okay, so one big problem, I now made two smaller ones. Okay, now we've got minus a half on the one side. We can take that across. So we're going to have root x plus 3 is less than 1 quarter x. And then it's going to become plus a half. So that will be plus 9 over 4. And then on the other side, I can take the half over to the other side there. So that's going to be 1 quarter x plus 7 over 4 minus the half. So plus 5 over 4. And that's less than root x plus 3. Okay, so one problem, I made two smaller problems, and then the root put by itself here. So there's the root by itself here, and the root by itself there. So now I can just square both sides. Okay, that gets rid of the root. Then we just have some quadratic equation over here, some quadratic equation over there. Your minus b plus minus, so on. You use your quadratic formula and you can solve for x. Okay, so once you square it out, I'll leave that for you to do for homework. just use your quadratic formula, solve for x for both of them. And you should get minus 2.6 is less than x is less than 8.6. With rounding, okay, one decimal place, you should end up with that. Okay, so using the quadratic formula, I'll leave that for homework. Okay, so just solve for x for both of those. Whatever the smaller one is, that will be minus 2.6. Whatever the bigger one is, that should be 8.6. Okay, with the rounding. All right. Any questions on that? No. Okay. Please make sure you go over your inequalities. Okay, No, it's not a joke. Okay, so with this error approximation, we're going to have a lot of error less than a half, for example. You want to solve for x. Or what is the minimum error? What is the maximum error? Okay, there's going to be quite a few inequalities with that. Okay, so please make sure you go over that. Okay, any questions on what we've done here? Okay. But please make sure you remember this here, this first line here. Whenever you talk about the error, it's always whatever the exact value is minus the approximation. Okay. You've done that in physics, with your experiments and so on. So it's always your exact. So what you should be getting, so the exact value minus the approximate value. Okay, that's the error. And if you want the error to be less than something, we always include the absolute value. So we don't worry about positive or negative error. We always put the absolute value. Okay, less than something, whatever that is. Right. Any questions on this? No. Okay. So that's the first part of the approximations, so linear and quadratic approximations. The next part of the section is differential approximations. So differentials and differential approximations. You should have seen this in your physics practicals, but we'll go through it just as the maths. Okay, but you should have seen this in physics. Okay, so firstly, what is a differential? Well, we've seen a bit of differentials before. So let y be some function of x. Okay, some differentiable function f. Then the differential, dy, so not dy by dx or anything like that, just dy by itself, is defined as dy is equal to, since y is a function of x, we write this as f prime of x dx. Okay, so it's a slight rewriting of the derivative that we know. So dy by dx equals f prime, and then we just take the dx over. So it's a very slight rewriting. So remember dy by dx is f prime, and we just take the dx over. Okay, so a very, very small rewriting of that. Okay, but this dy and this dx, we call those differentials. So dy, dx, dz, anything like that, that is called a differential. Okay, so what's the points of them? Okay, a small change in x given by dx. Okay, so if we have x and we have a very small change in x, we call that dx. very similar to the delta x, okay, but here we call it dx, is related to a small change in y given by dy. Again, very similar to the delta y, by the gradient at that point. So we know this already from dy by dx equals m, but you need to imagine that in the following way. So we got our function of x, and then if we do a very tiny triangle here, so we zoom in very, very small amount there, the horizontal displacement there, we call that dx. And then the vertical displacement, we call that dy. And we know that dy is given by f prime of x dx. Okay, at that point. So let's say at the point P. Okay. So if I give you the tiny displacement dx, and I ask what is the resulting change dy, then the resulting change dy is whatever the gradient at that point is, multiplied by that change in x. Okay, so gradient multiplied by the change in x, that gives you the change in y. Okay, again, you can think of it as m is delta y over delta x, right? Your average change. So delta y is m delta x. Okay, but that's for the average change. If you're looking at the instantaneous change, like we looked at before, average versus instantaneous, then the delta y becomes dy and the delta x becomes dx. Okay, we covered that before with the instantaneous rates of change. Okay, so that's the idea of relating dx and dy. So how do we use these? Okay, if we treat dx as a small error in x, okay, so we measure some x, whatever that is, then we're going to treat dx as the error in the measurement. Okay, so always think about your physics practicals. You measure x, there's going to be some error. The error we call dx. So if we treat dx as a small error in the x measurement, then the resulting error in the y measurement is given by dy. Okay, so you got your dependent variable and your independent variable. So x, that's the thing you are measuring. That's the independent variable. Then there's going to be some output from that. That will be y. So if there's an error in your x measurement, how does that relate to the error in your y measurement? Okay, and we'll have a look at an example now. So example, a cube has side length 30 centimeters. Okay, so you measure the side length of a cube to be 30 centimeters, but there's always some error. So with an error of 0.1 centimeters, okay, approximate the error in the volume measurement. Okay. So that's part one, and then part two, find the exact error. Okay, So again, think of a physics experiment. So you're measuring the length of something. In this case, it's 30 centimeters, but there's some error involved. Okay, you've all done the physics practicals with the errors, right? Yeah, so there's some error of 0.1 centimeters. That is in your measurement of the length of this side. Now, from your measurement, you want to find out what the volume is. Okay, V, the volume. But there's an error in your measurement of the length. If there's an error in the measurement of the length, there's going to be an error in the measurement of the volume, right? Okay, what we want to do is find what that error in the volume is. So how do we do that? Well, we know the volume of a cube is V equals x cubed. Yeah, so that's just the normal volume. What we want to do is approximate the error, the delta V given delta x. So we're going to take the differential dV. So dV is going to be dV by dx dx. Okay, this is just using the definition, dy is f prime of x dx. So it's just the definition. Now, what is dV by dx? That's going to be 3x squared. So dV will be 3x squared dx. Yes?
Since it's supposed to be 3x over 2.
Which one? No, we're not doing the derivative on both sides. We're doing the differential. So let's go back to here. We're doing this. Okay, yeah, not the derivative on both sides. We're doing the differential on both sides. So we've got V is f of x is x cubed. So dV will be the derivative of V dx. The derivative is only on the one side. Okay, so this is from the definition of the differential. Now we're going to do what we said here. We're going to treat dx as a small error in x, and then the resulting error, that's dy. In this case, it will be dv. So this dv, we're going to treat that as the error in v, so that will be delta v. Okay, right, from, again, your experiments, the error is delta x and so on. So dv, we're going to treat as the error delta v, and then we have 3x squared delta x. Yeah, you've seen that in your physics pracs, the delta x and so on. Okay, so this delta x, that is the error in x. And delta v, that is the error in v. Yeah, so now we just substitute. We know what x is. We said the side length of the cube was 30, and the error was 0.1. So we can just substitute. So delta V, that is 3 times 30 squared, and the error was 0.1. Okay, and this is some volume, so it's going to be centimeters cubed. Okay, that is the error in the volume measurement. So if you've got a cube and you measure the length, there's some error, okay, right, you know that from the practicals. Then if you're calculating the volume, that's the error in the volume. Okay, so if you were writing this down in your physics prac, you would put x plus minus delta x, right? You've all seen that? Okay, then you would have v plus minus delta v. Yeah, that's what we're calculating. So you measure x, you've got some error, plus minus delta x. You measure v, and you got some error, plus minus delta v. That's what we're looking for, that delta v. All right, any questions? No. Okay. And then this would be your experiment results. You would write that down. Do you use this in your physics pracs, the differentials? No. How do you get your errors then? The delta x and the delta t and all of that? How do you find that? You guess? Oh, they give you the equations for it. Okay. Yeah. This is how they get it. You use differentials to find that. Yeah. Okay. What about the exact error? So let's have a look at that. The exact error. So for the exact error, that's going to be delta V as well, because it's an error. This is going to be the volume with the error added on minus the volume without the error. Okay, so volume with the error minus the volume without the error. So the volume with the error is the length plus the error in length. So that's going to be x plus delta x cubed. So x plus delta x, that is the length with the error added on, cubed, that gives you the volume, minus the volume without the error. So that's just x cubed. Okay, so volume with the error minus the volume without the error. The difference, well, that's the error in the volume. Okay, so with error minus without error, that gives you the error in the volume. Okay, because that difference, that will give you the error that you're looking for. Okay, now this is not so bad. We can expand this out. Okay, or you can just substitute the values, but let's expand it out first. I want to show you something with that. Then we'll substitute. Okay, but you can just put in x, we know that's 30, delta x, we know that's 0.1. So you can do that. Okay, but if we were to expand it out, we would end up with x cubed plus 3x squared delta x plus 3 x delta x squared plus delta x cubed minus x cubed. Okay, so we're just expanding it out. X cubed in the front minus x cubed at the end, they can go. Okay, and now we're left with 3x squared delta x plus 3x delta x squared plus delta x cubed. Okay, now remember, these errors are always taken to be small. They're very small numbers. If I take a small number and I square it, it becomes even smaller. Like 1 over 10 is small. 1 over 10 squared is 1 over 100. That's even smaller. If I cube it, it becomes even smaller than that. So 1 over 10 is small. 1 over 10 cubed is 1 over 1,000. That's much, much smaller. So in the limit, when this delta x error goes to 0, the second term and the third term we can ignore. So we ignore that one, we ignore that one. They go to 0. Okay, now this is the exact error, and we've ignored those terms. What's left over? 3x squared delta x. That's exactly what we got here with the approximation. Okay, so in the approximation, we get 3x squared. Here, we didn't do any approximating. This is the exact error. We get 3x squared delta x plus some other terms. But if we ignore those terms, we get right back to the approximation we did earlier. Okay, provided delta x is small. So all of this only works if delta x is small. If delta x is large, this doesn't work anymore because we can't cancel. So note, this only works if delta x is small. It's small. So delta x squared, delta x cubed, and so on. All of those can then be ignored. Okay, so it only works if delta x is small. Okay, which it will be. For all of these examples, delta x will be small. Okay, another example. Okay, the radius of a sphere was measured to be 21 centimeters. Okay, so again, you imagine yourself in the lab, you're measuring the radius, you get 21 centimeters. With an error of 0.05 centimeters. Okay, so whatever you're using to measure this, there's that error of 0.05 centimeters. Okay, so that's your measurement. So what are we trying to get from this? Find the approximate error in the volume. So we measure the radius. We want to find out what the volume is. But because of this error, there's going to be some error in the volume. What is that going to be? Okay, find the approximate error in the volume measurements. Okay, and again, like before, the volume of a sphere, cone, cylinder, all of those shapes, please make sure you know them. They will not be provided. Okay, volume, surface area, all of that stuff. Okay, what do we do? Well, we've got a sphere, it's got some radius, and we want to find the error in the volume. So let's start off with the volume formula. What's that going to be? Yeah. Okay, that's the volume. Now we want to find the error in the volume. So that's going to be that differential dV. So we're going to write dV is, what's the thing we're measuring? The radius. So it will be dV by dr times dr. Okay. So again, the volume dV part, that's what we're trying to find the error of. We're measuring the radius. So it will be dV by dr, since it's the radius we're measuring. Okay, so dV, that will be the derivative with respect to r, the 3 comes down, so it will be 4 pi r squared dr. Okay, so that is the differential. Now this is going to approximate our error, so the delta V. So delta V, that's the error. The same as what you would write down in your prac, delta V. So this will be 4 pi r squared delta r. And we know all of this. We know the radius, we know the error, so we can just substitute. So this is going to be 4 pi. The radius was 21 squared. And then the delta r, let's go back up here, 0.05. Okay, and again, what is this? This is an error in volume. So the volume units, that will be centimeters cubed. Okay, please for the past section, the related rates, rates of change, the error approximation, all of this comes with units. Okay, please make sure you include that. So with rates of change, if it's the rates of change of height, that's meters per second or meters per minute. If it's a volume, then it's meters cubed or centimeters cubed. If it's an area, centimeters squared or meters squared, please make sure you include your correct units. For the quiz, the question asked for the rates of change of the height. Many students were writing meters cubed per minute. Okay, it is a height. Height is a length. Length is meters per minute. Okay, so everyone that wrote the meters cubed per minute, you got a -1 for the incorrect units. Okay, and if you didn't put the units, again, -1. So please make sure you have your correct units there. So just a little star there, units. Okay, please don't lose marks for silly mistakes like that. Okay, so we got that. And then number 2. So this was part 1, find the approximate error. Number 2, find the approximate relative error. Have you done relative error in your physics pracs? No. Okay, so I'll write it out for you. Find the approximate relative error. Okay. Relative error is very simple, so we'll do it for this example, but you'll get the idea. You take the error, whatever it is, in this case is delta V, and you divide it by whatever you're measuring. In this case, it's V. That's it. Okay, that's the relative error. So it's the error, delta V, divided by whatever you're measuring. So in this case, it will be V. So if you want the relative error in length, for example, then it would be delta X over X. Okay, so it's whatever the error is divided by whatever the thing is you're measuring. In this case, it's the volume. So that's the relative error. So it will be delta V from before divided by the volume of the sphere. Right. Any questions on the sphere example? Okay. Okay. Last example for today. Use differentials to find a formula for the approximate volume Okay, so all of these questions will be approximate volume or approximate area or anything like that. So as soon as you see this keyword here, you know it's this error section. Okay, so approximate volume, approximate speed, whatever the thing might be. Okay, we know it's this differential approximations. Okay, for the approximate volume of a thin cylindrical shell, okay, with height h, inner radius r, and thickness delta r. Okay, let's draw a picture to see what's going on here. So we've got a cylindrical shell. So what that means is we have some sort of cylinder like this. Yeah, you all know what a cylinder looks like. And to make it a cylindrical shell, we hollow it out. So the inside parts we remove. Yeah. So we've got a cylinder on the inside, and we remove that. Okay, so this inside part is hollow, and then we just have this wall over here. Okay, and then that inside bit, that's hollow. Okay, so that's what we mean by a cylindrical shell. Okay, it's like a pipe, and it's got some sort of thickness there. Okay, so it has height h, so that's h. The inside radius is r, so that's this bit here, r. Okay, up to that blue part, that's inside radius r. And then that white shaded part, that is delta r. So this thickness here, that's delta r. Okay. We want to approximate the volume of this cylindrical shell. So what we can do is start off with the volume of just a cylinder. Okay, what's that going to be? Pi r squared h. Yeah. Now, here we've got the error error or the thickness or however you want to think of it, delta R. So when we do the differential, it must be in terms of R because H is just H. There's no delta H. Okay, so we've got two variables here, but it's only the one that comes with the delta R. Okay, there's no delta H. So here we're going to have dV will be dV by dr, dr. Okay, there's no H, there's no delta H in the question. So it's just dV by dr, dr. Okay, so this is going to be dV by dr. Okay, the H, don't worry about that, that's just a constant. So it will be 2 pi r H. dr. Again, H, that's just a constant. We're not worried about that. Okay, so that's the differential. Now we're going to replace the dV with delta V and then the dr with the delta R that was given to us. So delta V, that's going to be 2 pi r H delta R. Yeah, and we're done. We've got that. So this delta V, that is the volume of the cylindrical shell, approximately. So this is the approximate volume of cylindrical shell. Okay, so that's it for the question. Now we're going to look at the exact volume and see how it compares. Okay, so this is just extra. Okay, the exact volume. Okay, so, in the test and stuff, if the question says find the approximate volume, don't carry on finding the exact volume. Please read the question. Okay, but this is just extra stuff. Okay, so the exact volume, that will be delta V. That will be V with the larger radius minus V with the smaller radius, because the smaller one we are removing. So with the larger radius, that will be pi r plus delta r squared h. So r plus delta r, that's the bigger radius, minus, and then this part here, the part that was removed, that just has radius r. So minus pi r squared h. Okay, we've got this thing squared, so let's expand that out. So that's going to be pi r squared plus 2r delta r plus delta r squared. Okay, h. Okay, the pi and the h we can multiply inside. So this is going to be pi r squared h plus 2 pi r h delta r plus pi h delta r squared. And then that last term on the outside, minus pi r squared h. Okay, first term, last term, they can cancel. And we're left with 2 pi r h delta r plus pi h delta r squared. Okay, now we're going to do the same thing as before when we looked at the cube. If delta r is small, delta r squared is even smaller, so we can ignore it. So we ignore that. So if we ignore it, this just becomes approximate, okay, because we're throwing stuff out now. So we're just left with 2 pi r h delta r. And if we compare this with the approximate, we see it's the same. Okay. So here, this was the exact volume. We throw away a term, so it's no longer exact, it's approximate. And this is exactly what we get over here. Okay, so whenever you're throwing stuff out, it's no longer exact, it's now approximate. And we can see it matches up. Okay, so this matches with what we had before. And you can check that for the other tutorial questions. So if the tutorial question says find the approximate error, you can use the differentials. Then as some extra work, you can then find the exact error and compare. but the textbook questions, they don't specify the exact error, but you can find that out as some extra work. All right. Any questions on this example? You're all good. Okay, so that will be it for the approximation chapter. So we're done with all of that for now. Next, we're going to be looking at curve sketching. So tomorrow we'll start with that. Sketching curves, polynomial curves to the power 3, 4, and 5. Okay, so fifth order polynomials. We'll do that tomorrow. Then next week, we're going to be looking at curve sketching with rational functions. So polynomial divided by polynomial. Okay, so for that, we're going to be looking at the vertical asymptotes and horizontal asymptotes and limits and all of that. Okay, so please make sure for next week you go over your limits. Okay, so when we do the vertical and horizontal asymptotes, you're going to have to know how to do the limits. Okay, that's for next week. Tomorrow, you don't need to know that. That's just polynomials that we're going to be sketching. Any questions on that? All good. Okay.